looks like it's on. For those of you watching online that didn't hear this, the project proposal is due today. And please make sure to turn in your project proposal on time. The usual late policy applies, which is that you have 5 cumulative late days over the entirety of the course. And then do make sure to carefully read the instructions for the project proposal and make sure to submit it through the course CMT website so that we can assign the peer reviewers. Remember to start early on homework 3. Hopefully all of you have already started on it. It's going to be due next week, of course, so do make sure that you get started early on it. It's not an exceptionally difficult homework, it's just that things take quite a while to run. So you don't want to finish up all of your code and not have the time for your experiment to complete before the deadline, so make sure you start early. Okay, so let's recap a little bit where we are since last time. So in the last lecture, we talked about how if we know the transition function or the dynamics of the system, how we can choose good actions. And we talked about choosing good actions using stochastic optimization algorithms, using Monte Carlo tree search, using the derivatives of the dynamics with iterative LQR, and so on. So these are all different ways that we can choose actions if we know the transition probabilities or the dynamics of the environment. So today, we're going to talk about what happens if we don't know the dynamics of the environment, but would still like to employ some of these planning or optimization techniques. We're going to talk about how we can learn global dynamics models from data and what are some of the considerations that we have to take into account there. And then in the second half of today's lecture, we're going to talk about how we can learn local dynamics models from data, ones that don't try to estimate the transition everywhere, but only in the region close to your current policy. And then on Friday, we're going to talk about how we can learn dynamics for higher dimensional observations like images. So today we're going to mainly focus on some of the theory and algorithms, and then on Friday we'll talk about how to take that into the world of deep learning and apply it to high dimensional and complex problems. And then the following Wednesday we'll also bring in policy learning, and we'll talk about how we can combine model-based RL and optimal control with policy search to actually train policies. For today, we're going to mainly focus on learning models and then using them for planning. So today's lecture, we're going to start with an overview of model-based reinforcement learning, where we'll talk about some variants, where maybe you learn only the model. We'll briefly touch on learning the policy, but we'll really go into that in more depth next week. We're going to talk about what kinds of models we can use, global models and local models, and what that means, learning local models with trust regions, and we'll do a little bit of math and derive actually the dual gradient descent procedure, which is nice in other parts of RL also. So the goals for today's lecture will be to understand the terminology and formalism of model-based RL, understand the options for the models that we can use with model-based RL, and we'll talk about a few different classes, both deep nets and ones that are not deep nets, and then understand some of the practical considerations for model learning. So there's not going to be actually all that much deep RL today. This is really going to be more about the basic concepts and algorithms, but we'll see kind of more fancy deep net stuff starting on Friday. Okay, so why should we worry about learning a model? Well, we saw last week that we can solve nice, relatively simple constraint optimization problems like this one, which we talked about for LQR, and choose optimal or near optimal actions. But to do that, we need to know the derivatives of our cost or reward, and the derivatives of our dynamics. And the derivatives of our dynamics come from the model. So last week we assumed that these were known because maybe someone had written down the equations for you, or you had access to a simulator that you could use finite differences with. But you need to get these from somewhere, so you can get them from learning the model. Similarly, if you want to use Monte Carlo tree search requires you to forward simulate multiple rollouts. Where do you get these rollouts? Well, you can run them, again, through your learned model. So if you don't know the dynamics, maybe you don't have access to the emulator for the Atari games, you just get a bunch of trials that you can play, then you have to learn those dynamics in order to do the rollouts to run something like Monte Carlo tree search. So if we knew the dynamics, like for example, if they're deterministic, if we knew f of ST AT, we could use the tools from last week. or the probability in the stochastic case. So let's learn this from data, and then let's use it for planning using all the tools from last week. That's the basic idea. So that actually yields the simplest, kind of the baby version of model-based RL, which I'm going to call model-based reinforcement learning version 0.5. This is not actually the name of this thing. This is just something I'm attaching to the lecture, in this lecture. You're not going to find version 0.5 in a textbook, but just so that we have something to call this thing. So model-based reinforcement learning version 0.5 is going to work like this. You start off with some kind of base policy, which might be just a completely random policy, and you run it, and you collect data. And it's also worth mentioning that maybe you didn't actually run a policy, maybe someone just gave the data to you. Maybe this is data that someone else obtained, maybe from a person driving a car or something. So you get your data somewhere, and the data, concretely, consists of tuples of transitions. It consists of a state, an action, and the next state that you landed in after taking that action. Of course, if this is collected by actually interacting with the environment, these transitions are probably arranged into trajectories, which means that the S prime for the first data point is the S for the second data point. But we're not actually going to require that. It's just, we're just going to assume that everything consists of these little tuples. Then, in step 2, we're going to train a dynamics model to minimize some prediction loss. If we had a stochastic model like this one, the P of st plus 1 given st at, then what we would probably do is maximize the likelihood, maximize log P of s prime given s comma a. If we have a deterministic model, then we can have maybe some kind of regression loss like this. So we have a few different choices. Actually, the regression loss is just maximum likelihood for a Gaussian distribution, so they're all kind of the same. And then step 3, use this learn dynamics model for planning to choose your actions using the tools from last week. That's it. So this is kind of the simplest thing that we can think of that does model-based RL. So number 3 is just do the stuff from last week, and number 1 and 2 is just do supervised learning. So does this work? Well, in many cases, the answer is yes. So this basic outline is essentially how system identification works in robotics. So system identification means that you know roughly how your robot is built. You know that it has 2 arms and 2 legs, and you're trying to figure out some physical parameters of that system, maybe the masses of those parts. Some care should be taken to design a good base policy. So if your base policy just sort of sits in one place and doesn't ever do anything, like if it only ever outputs action 0.0, then you will never learn anything about any of the other actions. So you do need a base policy that explores the environment sufficiently to sort of exercise all the different modes of the system. And this kind of approach can be particularly effective if we're using a small hand-engineered representation for our model. So if we're not training like a huge neural net to predict the next state, but maybe we are fitting some small number of parameters. Maybe like in the robotics example, we know the lengths of the robot, but we just need to figure out their masses, or roughly the kinematics that govern your car, but you want to fit a single number for how powerful the engine is or something like that. So if you have a small number of dynamics parameters and you believe that your model is accurately specified, meaning that the right answer is in your hypothesis class, then this kind of approach can work decently well. In general, however, the answer is no. And the answer is no, actually, for a reason that we already saw back when we talked about imitation learning in the beginning of the course. So let's say that I live in this world, and my goal is to get to the top of the mountain, to the tallest place. So step 1 is I'm going to run my base policy. And let's say my base policy is random. So my base policy is going to walk around on the hillside like this. And then step 2, so this is my base policy, pi 0. Step 2 is to learn my dynamics model. And my dynamics model is going to predict how high up I'm going to be. So when I'm walking around on the hillside here, it looks like every time I go to the right, I get higher up, which is good. So I'm going to learn a very simple model. It's going to say, well, going to the right gets you higher. So then in step 3, when I actually plan through this model and actually choose actions, I'm going to be in for a nasty surprise. Because while the pattern I learned over here holds true for a while, it doesn't actually hold true everywhere. So I collected data from a particular distribution over states. induced by my policy pi0. So I collect the data from p pi0 of s, and I use that data to fit my model, and then I plan through that model, and I'm in for a bad time. So does anyone have any guesses as to why this problem occurs? What's the problem here? Why do I end up falling off the cliff? Yeah?
The step size is too big.
That is, yes, that is part of the issue, yeah, that I'm kind of planning through the model a little deeper than I should, yes.
Is the problem with the reward function?
Is the problem with the reward function? Well, so I kind of omitted all the discussion of reward functions here, but you can imagine two ways to deal with reward functions in this kind of algorithm, and this is worth mentioning. If you fit a dynamics model to, let's say with some kind of maximum likelihood loss, you can either assume that you already have a reward function that you can evaluate in terms of the states, or if you don't have the reward function, you can fit it in the same way. The two are actually kind of isomorphic to each other, because if you don't know the reward function, you can just pretend that there's some other state variable, and the reward is just equal to that state variable, and you can fit it in exactly the same way as this. So I kind of intentionally gloss over reward functions, but they're basically a non-issue. You treat them the same way as states.
I think the problem is in base policy.
Right, so this is maybe getting a little bit at that point, that the problem is maybe with the base policy. Like somehow that base policy didn't tell us what we needed to know. Was there another answer back there, yeah?
Local optimum versus global optimum?
Maybe a local optimum or a global optimum, maybe. I would posit that even if you have all of these problems be convex, you would still have this issue. So the issue is indeed with the with the base policy. So the base policy gave you data from some distribution p pi0 of s. But when we actually run our planner, we see different states. We don't see the states that are sampled from p pi0 of s because pi0 was a bad policy. It was some kind of random thing. Hopefully when we run our planner, we take better actions. So we see states that are distributed according to the state distribution of a better policy. Or a worse policy, but just a different one, that's the point. So we see data from something else, which I'm going to call p pi f. Pi f is basically the policy that is induced by using the model f and then planning through it. So now that we see that we're getting states from p pi f, does anyone have another guess as to what the issue might be? Right, so the answer, for those of you that didn't hear, is that, well, these distributions are not the same. And when these distributions are not the same, even if we generalize well, in terms of our dynamics model, to states from p pi0, we have no guarantees about generalizing well to states from p pi f. Right, so any kind of supervised learning procedure, if it's a good supervised learning procedure, it can usually give you some sort of guarantee that if you see new inputs from the same distribution as your training data, then you will have low generalization error. But supervised learning will not give you guarantees on your generalization error from some other arbitrary distribution. So if you've never seen, the cliffside here, you've only seen the mountain, there's no possible way that the model you learned on the mountain will help you understand what happens on the cliffside. So it's a distribution mismatch. Yes, question back there.
Can't you just solve this problem by doing something like Dagger then, where you just change the base policy?
Right, so the comment in the back was, well, we've seen this before. Can't you just use the same tool that we used in imitation learning, which was Dagger, where you aggregate data? And the answer is yes. And that's exactly what we're going to do. So the distribution mismatch problem becomes exacerbated as we use more expressive model classes because they can fit really well to p pi0, but then of course will fit worse to p pi f. So what we do is we aggregate. The way that we do better is by trying to make p pi0 equal to p pi f. And we saw this problem before with imitation learning, where we needed to make the expert's distribution and the learner's distribution match. And the way we did that was not by having a perfect learner, but by actually changing the data distribution. So instead of trying to make p pi f match p pi0, which here would defeat the point because it would give us a bad policy, we're going to go the other way. We're going to take our data distribution and change it so that it matches what we get when we run the planner. So this is model-based reinforcement learning version 1.0, and the reason I call it 1.0 is because this is an algorithm that you might actually want to use. Like this is an algorithm that will, under some circumstances, actually give you good solutions. So you run your base policy just like before. Then you're going to learn your dynamics model using data from that base policy. Then you're going to use it to plan and choose actions. And then you're going to execute those actions and add the resulting data to your data set. Just like in Dagger, when we run our policy and we collect more data, we label it with the optimal label. Now here, of course, the label is not the action. Here, the label is the next state. So it happens to be very, very easy to get the optimal label because the world gives it to you. So you don't need to know the optimal action. You just need to know the correct next state, which you get just by acting in the world. And then you repeat this process. So you relearn the dynamics model using the new data, use it again, collect more data, relearn the dynamics, and so on and so on and so on. And if you repeat the process, if you're always adding more data using the policy derived from your latest model, then eventually your data distribution will match the distribution of states that you see when acting according to your model. Does anyone have any questions about model-based RL version 1.0? Okay. So where have we seen that before? Well, this is basically the model-based RL version of Dagger in a sense. Now, there is a little bit of an additional catch, which is, so this procedure will address the distribution mismatch problem, and it will eventually get you decent results. But you can actually get decent results a lot faster with a small modification. So what if we made a small mistake? So what if we have a model that's pretty good, but not perfect, and we make a small mistake while we're executing our actions? Small mistake meaning that the actions that we planned don't actually get us quite the state that we wanted. It's a little hard to see in this mountain example, but I'll give another example, which is if you're driving a car down the road. And let's say that you estimate that, well, if you keep the steering wheel straight, okay, the right answer is if you keep the steering wheel straight, the car will go straight. But your model made a small mistake. It says, well, if you keep the steering wheel straight, it'll actually drift a little to the right. So what you should do is you steer a little to the left. Just a small mistake. So then you'll steer a little to the left, and after you steer a little to the left, maybe your model will still say, well, okay, you might drift to the right, so keep steering a little to the left. And the errors, each of the individual errors that the model makes are really, really tiny errors. But because they're accumulating, because you're acting with respect to that model, those compounding errors might eventually lead you to disaster. So the issue here is that small errors in the model can manifest in big errors in the resulting behavior. There's actually a pretty simple fix to this, which is that if you see the car start drifting, if you see it start going a little to the left, what you should do is you shouldn't keep following your plan. You should actually generate a new plan in light of the fact that you're now not going in the direction you wanted to go. So if you generate a new plan, probably once you deviate enough, the model will understand that, okay, you're going to actually go off the road and will correct you. So that's a very tiny modification to the model-based RL version 1.5. The modification is the following. We're still going to run our base policy to collect our data. We're still going to use it to learn the dynamics. We're still going to use it to plan to choose the actions. But then, instead of executing all of the actions that we planned, we'll actually only execute the first action that we planned, see which state we land in, and then plan again. So if I were to draw this on the board, what that means is I start over here, I generate some plan, this is what I want to do, then I'm going to execute only the first action on that plan, and maybe I landed in the wrong spot, and then from here, I'm going to generate a new plan which will hopefully correct that mistake. And then I'm going to execute that action and repeat. This is referred to as model predictive control. And model predictive control is a good idea when doing model-based reinforcement learning because when you're doing model-based reinforcement learning, your model is usually imperfect, which means that you will usually make at least small mistakes. So by replanning, you will actually enable your policy to correct those mistakes before they become major problems. And with suboptimal models, with slightly imperfect models, this can get you good results much sooner than if you were to wait until the segregation procedure actually gets you the perfect model. And then, of course, just like in version 1.0, you append your transition to the data set, and periodically, well, of course, you repeat this process every time step, and then periodically you relearn your whole model. So this helps with model errors. And in fact, on homework 4, you'll actually be implementing an algorithm that makes use of this procedure that fits models and then iteratively replans. So how do we plan? Well, we use everything that we learned from last week, but one thing that's maybe worth noting is that the more often you replan your actions, the less perfect each individual plan needs to be. Because now you're not actually going to be using all of the actions that you planned. You're only going to execute the first action. All those other actions that you plan, they're just there for you to figure out what the right first action is. So in practice, if you're replanning every time step, you can often get away with much weaker planners than if you wanted to construct the perfect plan once and then execute all those actions. So you can use shorter horizons, you can use computationally faster algorithms, even things like the random sampling that I talked about last week can actually work decently well if you replan every time step. They will not work well if you generate a huge long plan once and then commit to it. So if those of you that remember the video I showed last week, this of course didn't use a learn model, but this here, the model is intentionally incorrect. The hopper is actually lighter than the model thinks it is, and here it's heavier than it thinks it is. And this algorithm is using iterative LQR, and it's replanning every time step. And the replanning is what allows it to correct for the mistake. So even though it thinks the hopper is much lighter or much heavier than it really is, it can still stabilize it to get it to stand up just by replanning. Okay, so the downside with all this is that it kind of seems like a lot of work. So for example, if you want to use this to like play video games and you use the Monte Carlo tree search algorithm that I described last week, you're basically running all of Monte Carlo tree search from scratch every single time in step number 3. And that can be pretty expensive. So the cost of that can really add up. To foreshadow something that we're going to discuss next week, what you can do is you can actually use procedures like this that are computationally very expensive, but then actually distill them down into a policy, actually use them to supervise a policy as though you were supervising with demonstrations. This is what's done in this paper, for example. So you could run Monte Carlo tree search, get your actions, execute them, and so on, but only do this during training. And then afterwards, when you want a nice computationally cheap policy to actually run at test time, you can just take all of the actions that you generated while using your computationally expensive planner and use them to supervise a policy, which can be much cheaper to execute. So that's a nice way to get around some of the hard work, and we'll talk about that a little more next week. Okay, any questions about version 1.5? Yes?
You sort of intuitively mentioned there could be this like scale where you sort of sometimes replan and sometimes don't. But
yeah.
That isn't written down? Is that
Yeah, so there's a very straightforward generalization of this scheme where you say, well, okay, maybe I'm not going to replan every single time step. Maybe I'm going to replan like every 5 time steps or every 10 time steps. And that's pretty straightforward. And the trade-off usually is that the more often you replan, the weaker your planner needs to be. And the less often you replan, the stronger it needs to be. Okay, now another thing you could do is you could say, well, let's not bother doing all this business and then try, maybe if you really want a policy in the end, maybe let's not bother doing this business and then training the policy. What if we just directly try to use our model to train a policy? So you could do that. You could actually set up a differentiable computation graph if you represent your model with some differentiable function class like a neural network. And this differentiable computation graph is going to have nodes for your reward, it's going to have nodes for your model, and it's going to have nodes for your policy. Here I'm assuming everything is deterministic. You can generalize to stochastic versions too, using something called the reparameterization trick, which we'll cover much later in the course. But for now, let's say everything is deterministic. If you've learned F with something like a neural net, and you want to learn something like a neural net for pi, all of these are differentiable functions, so you can compose them into a computation graph and use your favorite autodiff software to compute the derivative of the policy parameters with respect to R, and then backpropagate. So that's a way that you can actually train policies using models. The resulting algorithm, which I'm going to call version 2.0, not necessarily because it's better, but because I need a different number, is going to work like this. Step 1, you're going to run your base policy just like before. Step 2, you're going to learn your model. The model is learned in the same way, just with maximum likelihood or regression. But then step 3, instead of planning, what we'll do is we'll actually have a second optimization where we'll backpropagate through F into the policy to optimize the policy so as to maximize the reward function. And then step 4 is you're going to actually just run the policy, collect the resulting data, and append it to your data set to address the distributional shift problem, and then repeat. This is a viable way to train policies. Unfortunately, as I described it on this slide, at least for neural network models, it often will not work very well. Part of why the very basic naive version won't work very well is because you kind of get the world's worst exploding or vanishing gradients problem. So those of you that are familiar with recurrent neural network training might know about the term exploding or vanishing gradients. What that refers to is the fact that when you have a long temporal sequence like this, let's say there's some really big reward at the end here, the derivative of that reward with respect to the action that you took at the very beginning requires you to apply the chain rule through all of these nodes. Now, if you imagine what the chain rule actually will look like here, you'll have the derivative of st plus 1 with respect to st80. You'll have the derivative of st with respect to st minus 1, or the derivative of at with respect to st minus 1, and so on and so on and so on. So what you end up with is you end up with a lot of these partial derivative terms. You basically end up with, df d a capital T. You get d pi d S capital T, you get df, dA, t minus 1, and so on and so on and so on. And each of these terms, it's some kind of Jacobian. And if each of those Jacobians has eigenvalues that are, let's say, larger than 1, then you multiply a whole bunch of them together, and you get some really gigantic numbers. If they have eigenvalues that are less than 1, you multiply a bunch of them together, and you get numbers that are all essentially 0. So this is what is often referred to as the exploding or vanishing gradients problem, which means that the gradient with respect to the policy parameters here at the beginning might be either really, really gigantic to the point where it overflows, or really tiny to the point that you're not learning anything. In the world of recurrent neural networks, exploding and vanishing gradients can be solved through a number of approaches, many of which involve actually changing the representation of the neural networks. If you've heard of the LSTM, the long short-term memory, it's a particular design for the network that has better gradients. Unfortunately, we don't have the luxury of employing that trick here because our model has to actually represent the dynamics of the environment. So we can't just change our model to make things easier to learn because the model has to actually be a correct model. It has to actually satisfy the subjective. And if the real dynamics of the environment have big or small eigenvalues locally, then our model will also. So in practice, first-order derivatives through these kinds of things can work poorly. There are many tricks to make them work better, and we'll discuss some of those. In fact, some of them we'll actually allude to today. Does anybody have any questions about version 2.0? Okay. So let's summarize what we learned about model-based RL so far. We talked about kind of a version 0.5, which is kind of a thought exercise for the purpose of this class, although it is a viable way to do things like system identification with very, very small model classes. So version 0.5, you collect your random samples, train the dynamics, and then plan, and that's it. The benefit is that it's simple, there's no iterative procedure. The downside is that you get this distribution mismatch problem. And for expressive, powerful model classes, the distribution mismatch problem basically makes this method non-viable. Version 1.0, which was the first version that generally tends to work in practice, is to iteratively collect your data, replan, and then collect more data. So this is the idea here is that you're going to collect more data using a planner that is using the model that you train on your old data, which means that you'll collect more data for the states that you'll actually visit with that planner, which will address the distributional shift. So the benefit is that it's still simple, it solves the distributional mismatch problem, but the downside is that the open loop plan might perform poorly, especially in stochastic domains. So that's where we got to version 1.5, which is a slight improvement on version 1.0, where you do exactly the same thing, except that you replan every time step, and that lets you deal with this kind of drifting problem. This makes you robust to small model errors. The downside, of course, is that it becomes computationally much more expensive. So the computational cost, you can reduce that a little bit by taking advantage of the fact that if you're replanning all the time, you can use a weaker planner, a planner with a shorter horizon, or you can try to amortize that cost by actually distilling things down into a policy. And then version 2.0, which is really kind of a different algorithm, was to do all the same stuff, but now actually use the model to directly train the policy by backpropagating through it without ever having to run a planner anywhere. and use that to get your policy. So the big benefit of this is that it's computationally very cheap at runtime because you're no longer doing any planning. All the computational cost has been offloaded to training, but the downside is that the naive way of doing this can be numerically very unstable, and we'll discuss much better ways to use a model to train a policy later on. But before I do that, I want to mention some examples of works that have done model-based RL in the past, including ones that actually, implement this version 2.0, the thing that I said is numerically unstable. So this is actually a slightly older paper. This is, I believe, from 2011, called Learning to Control a Low-Cost Manipulator Using Data-Efficient Reinforcement Learning. And the idea in this paper was to use reinforcement learning version 2.0, but with a very particular class of models that makes that backpropagation fairly tractable and actually fairly stable. So the idea is the following. Just like in the version 2.0 algorithm I described, you're going to run your base policy to collect your data. Then, what you're going to do is you're going to train a dynamics model, but a very particular dynamics model. So the dynamics model used in this paper is something called the Gaussian process. A Gaussian process is a Bayesian non-parametric model. You can think of this as kind of a Bayesian non-parametric generalization of linear regression. But the nice thing about Gaussian processes is they give good uncertainty estimates. So they will tell you for a particular state action tuple, not just what the most likely next state is, but what the distribution over the next state is. And then this paper proposes a very particular way of using the model to backpropagate into the policy to improve the policy. And I'll describe that a little bit more in the next slide. This isn't a course on Gaussian processes, but I do want to describe this procedure because we'll talk about some deep RL model-based methods next time that make use of similar ideas. And then step 4, of course, is just run that policy, collect more data, and then append that data and retrain so that you address the distributional shift problem. So the way that these guys do step 3 is a little bit interesting. So for them, the model is stochastic, which means that it gives them probabilities over the next state. And what they do is they formulate an approximation to the way that you compute state marginals. So in general, if you have some complicated distribution over P of S prime given S comma A, then even if your initial state distribution is something really simple like a Gaussian, your distribution over the second state or the third state will be some really complicated monstrosity. So what they do is they exploit the fact that for a Gaussian process, if your current state marginal is Gaussian, you get a non-Gaussian distribution over the next state, but you still have a closed form expression for it. After that, you don't have a closed form expression. So because P of ST plus 1 is no longer Gaussian, now if you apply the Gaussian process one more time and try to get P of ST plus 2, it's going to be some disaster. But P of ST plus 1 is non-Gaussian, but with a closed form expression. So what they do is they compute this P of ST plus 1, and then they project it to a Gaussian, just with moment matching. So they say, let's figure out the mean and the variance of this thing, and let's just declare that a P of ST plus 1 is Gaussian, even though it isn't, just with the same mean and variance. So that means that if the green distribution is what you predicted, is what you would get at ST plus 1, you would fit this blue curve to it to say, okay, that's my Gaussian approximation to ST plus 1, and let's repeat the process. So the Gaussian process gives them some kind of fancy distribution that they convolve with the Gaussian state marginal to get a non-Gaussian next state marginal and then project. Now, the other property they exploit is that computing the expectation of the reward under a state marginal is easy if the state marginal is Gaussian and if the reward has some nice convenient form. Basically, there are a number of functions that have analytic closed form expressions for their expectation under a Gaussian. Many polynomial functions have that form. So, quadratic functions, very easy to compute the expectation of a quadratic under a Gaussian without any kind of sampling, just analytically by writing down an equation. So you can analytically write down an equation for the expectation of the reward. You can approximate the transition probabilistically using this moment matching. So both of these are actually differentiable operators, so you can compose all of them together, push gradients through them, and then take the derivative of the expected reward at every single time step with respect to the policy parameters. So then you just write down the sum of the expected rewards and differentiate. And it turns out that for Gaussian processes, with this particular moment matching trick, this does actually give you decent gradients. In many cases it doesn't, but for this particular setting, it actually does. So here's the video of their demo. They use this method to control a little low-cost robot arm to put blocks on top of other blocks. So they have a little cheap little camera, they have a wobbly little robot, and then they're going to use their wobbly little robot to put wobbly little blocks on top of other blocks. So this is their robot controlled by their policy learned via this Gaussian process dynamics model. Okay. So this maybe gets us thinking, well, okay, so what kind of models should we use? I mean, these Gaussian process things seem kind of nice. Are there other options? What are good options? What are the pros and cons of different options? So actually, oddly enough, Gaussian processes have been extremely popular in model-based reinforcement learning, which is why I mentioned them. We can also use deep neural networks for models, and of course, you're going to have a homework assignment on that. And there are also other model classes that are worth knowing about. So using a Gaussian process as a model just means that your Gaussian process has the state in action as the input, and the next state as the output. One of the big advantages of Gaussian processes is that in sharp contrast to neural networks, they're actually very data efficient, which means that they can give you decent predictions from only a very small number of samples, which can be quite useful in model-based RL, because in model-based RL, when you're first starting off, maybe on the first iteration, you don't have very much data, and you'd like to make sure that you avoid overfitting. And the trouble with Gaussian processes is that they're not very good at representing certain types of functions, especially non-smooth functions can give you a lot of trouble. If you want to get more into the details of this, I recommend a book called Gaussian Processes for Machine Learning by Carl Rasmussen, which discusses these kinds of things in detail. The other big challenge with Gaussian processes is they can get extremely slow when the data set is large. So they're great when the data set is small, but they're not so great when the data set is large. It's kind of exactly the opposite of neural networks. Neural networks are very efficient with large data sets. So if you want to use neural network dynamics models, same deal. The input is the state in action, and the output is the next state. If you have continuous states and you use this kind of mean squared error, Euclidean distance training loss, that basically corresponds to the log probability of a Gaussian distribution. But in general, you can use any other kind of maximum likelihood estimation to train your model, including models that output more complex distributions like multimodal distributions, for example, the mixture density networks that we talked about when we discussed imitation learning. So there's a lot of flexibility in what you can do here. The big advantage of neural networks as dynamics models is that they're very expressive and they can use a lot of data. So very expressive means that they don't have this issue. They can basically represent whatever crazy function you want. But of course, the price of being able to represent any crazy function you want is that you typically need more data to actually learn that function. So the downside is that they end up being not so great in low data regimes. There are many other classes of models that have been explored in the literature, including things like Gaussian mixture models, Dirichlet process mixture models, and so on, that are all kind of from the pre-deep learning era of machine learning techniques. For example, you can train a Gaussian mixture model, and then when you have a new state in action, you figure out which cluster the state in action are in, and then condition that cluster to get your predictions. So there's funny stuff like that you can do. There are many other classes of models, including domain-specific classes. So if you know something about your system, if you know that it's maybe a robot with a particular physical linkage, or you know that it is some kind of inventory management problem where there's trucks coming in and trucks coming out, and you can write down some equations about how they behave with a few unknowns, and then just optimize those unknowns, that can also work very well as a model. And then all of these things that I described, they generally deal with fairly, so far for the purpose of today's lecture, with fairly low dimensional representations of state. If you want to go to really high dimensional representations of state, like images, then it's also really important to use high capacity models that can actually handle that. And here, usually neural networks will end up being your only really viable option, although people have explored non-parametric techniques also for high dimensional observations with kind of mixed results. So that's kind of the quick overview of model classes. Question back there.
If you're learning your representation of state and policy on the fly in a neural network, like not in a small tabular setting, does the lack of like a fixed reference point of state make it difficult to learn your action around it?
What do you mean by fixed reference point?
So as you're experiencing the world, you're learning how to represent state efficiently while you're learning to represent action dependent on the state. So if you're learning both of them simultaneously, and let's say your representation of state changes because you have some more experience, all of your policy that was dependent on that old representation is now thrown off a little bit.
Right, so typically when people do model-based reinforcement learning, the model and the policy are actually kept as completely separate function approximators. You could imagine combining them. You could imagine, let's say, having the same feature layer shared between the model and the policy. I haven't actually seen people do that. I would expect that that might cause some trouble because, the reasoning here is a little bit more involved, but basically with a little bit more derivation, a little more than I'm going to go to in this lecture, you can actually show that model-based reinforcement learning, if you're learning a policy, represents a saddle point problem. It's a kind of an adversarial optimization where your model is trying to fit the dynamics of the world, and your policy is actually trying to essentially throw it off. It's trying to exploit it. So if your model will erroneously predict something good happening somewhere, the policy will attempt to do that. And because this is a little bit of an adversarial process, generally it's probably not a good idea to share representations between models and policies because they're basically trying to do two diametrically opposed things. All right, last example I wanted to show before the break was an example paper that does model-based RL version 1.5, and what you'll actually be implementing for homework 4 is very closely related to this. So this is a model-based RL version 1.5, which, to remind you, consists of learning the dynamics model, planning through that dynamics model, and then replanning every single time step, and then, of course, doing the data aggregation. And in this work, the dynamics models are represented by neural networks, and what the authors here did is they actually used this method on some of the Mujoko benchmark tasks, similar to the ones that you guys all experimented with in homework 1, but then tried to see whether they could use the model-based RL procedure to get them to do some more interesting things. So this is the video. The interesting thing about model-based reinforcement learning is that once you learn the model, if the model is a good model, you can use it to accomplish different goals. So here, the swimmer was trained to swim, but now at test time, it's given these waypoints and it's told, well, let's do this kind of elbow-shaped turn. Now, of course, it's not as graceful as the example that I showed last week, which used a ground truth model. This is not a ground truth model. It's a learn model, so it's a little more sluggish, but it generally gets the right idea. So it takes a little bit of wiggling to get there, but eventually figures out how to clear waypoints in a new pattern that was not seen during training. And here's the same thing with the quadrupedal ant. So some of you probably played around with this in homework 1. So here they train a model that goes in one direction and then optimized a plan with MPC to follow a different path. Okay, at this point we're going to take a 3-minute break and reconvene at 10:55, and then I'll talk about local models.
How do the policy changes after we learn a model, for example, in version 1.5? It doesn't mention how to change the policy, right?
So in what I discussed, the only algorithm that actually learns policies explicitly was the very last one.
Yeah.
All of the others just learn the model and use it to plan.
Yeah.
And you can go either way. There's pros and cons to both. The benefit of just learning a model and using it for planning is that you don't have to deal with having a second function approximator.
Yeah.
The benefit of learning the policy is that you have much lower computational cost at test time.
Okay.
And you also don't have to worry about how to design your planner.
Yeah. So after we learn the model, what's the policy?
The policy is just the policy induced by the planner. So it's, what is a policy? A policy is a piece of code that takes in a state and spits out an action, or a distribution of actions.
Yeah.
So here that piece of code happens to be a planner.
Oh, okay, thank you.
That's it, yeah.
As a follow-up to the question about how often you replan in 1.0, is there a way to do that sort of based on perception of error? Sort of.
Probably. I can't say I've seen anybody do that, but yes, I would imagine that could work. I think part of why people usually don't bother with it is that, the planner has some considerable computational cost, but that computational cost is probably not varying drastically time step to time step. So if you say, well, okay, I'm running my system in real time, it has this particular computational budget, that computational budget is basically going to limit how often I replan, so there's not really any point in waiting longer than that. That's, I think, why it hasn't been explored too much. But if there's some particular setting where you believe this will make a difference, I think it would make total sense.
Sort of makes me think of how, you know, some people in management science say, well, if our predictions are matching our plan, we kind of we proceed as if things are okay.
Right.
But when our predictions start to be widely varying, it sort of ties into the difference learning to some
I think it's reasonable. It's just in a practical setting, at least for like real-time systems, it's a little weird to imagine that that would actually be a constraint. All right, let's continue. So, in the second half of today's lecture, I'm going to talk about local models. So far, all of the model-based RL ideas we discussed involve training a model, f of st, at, which it can be represented in different ways. It can be represented by a big neural network, it can be represented by a Gaussian process, whatever. But the point is that this thing is supposed to be a global model, meaning that our goal is to get this thing to model the dynamics of the world accurately everywhere. So when we do, for example, this is the 1.0 version of the algorithm, we're just adding all additional data to our data set and then retraining this thing so that in the end, if we visit all the interesting regions, F will be a good model in all the interesting regions. The trouble is that any kind of plan or a policy, if it's optimized against that model, it will seek out the places where the model is erroneously optimistic, meaning that if the model thinks that you will get a high reward somewhere, even if it thinks so incorrectly, the planner will want to go there. And since every model will make some mistakes it'll conclude things are better than they really are, some it'll conclude things are worse than they really are, the planner will go and find the places where the model erroneously thinks things are better than they really are. We'll talk about a number of solutions to this problem also next time, next lecture, but today we're going to talk about one specific solution, which is to basically avoid the need to find a very good model that is globally accurate, but instead stick to estimating the dynamics only in a local region around your current policy. So in some tasks, the global model is actually much more complex than the behavioral skill that you want to learn, and it's actually completely unnecessary to learn a model that is globally accurate everywhere. For example, if I want to be able to hold up a cup filled with water, the physical phenomenon involved, the contact between my fingers and the cup and the sloshing around of the water inside the cup might be very complicated, but the particular strategy that I need to deploy to hold this thing is very, very simple. I just need to squeeze my hand and it will stay in place. So there are cases where the policy is actually a lot simpler than the model. There are also cases that have the opposite property, where the policy is more complex than the model. So maybe if we're in a case where the policy is simpler than the model, maybe we're better off only learning a model that is locally accurate rather than globally accurate. So we're going to talk about local models, and we're going to talk about local models in the context of a variant of the LQR algorithm that we covered last time. This discussion is going to be a little more technical, but I want to explain first a little bit some of the reasons why I like to go through this part in lecture. It's not just because the particular algorithm here is actually necessarily a great algorithm. It's because some of the mathematical tools that we use to derive this are also broadly useful in other parts of reinforcement learning. So partly this is a discussion about fitting local models, but partly it's also an opportunity to go over some of the mathematical tools like KL divergence constraints that pop up again and again in other parts of reinforcement learning, and that we've seen a little bit of already when we discussed advanced policy gradients. Okay, so for local models, what we're going to do is we're going to try to solve this kind of constraint optimization problem that we had before when we talked about LQR. Because of that, now the dynamics F is unknown, which means we have to learn it. Now, for LQR, you don't actually, like the important thing is not so much that you need F, it's that you need its derivatives, right? You need df dx and df du because that's what we're going to plug in as our approximations for the linearized dynamics. So really the game is much more about getting accurate derivatives than it is about getting an accurate estimate of the function. You can get, if you just want to locally evaluate the function, you can run your policy in the real world and see what happens. But you can't get derivatives directly from the real world. So how can we figure out what df dx and df du actually are? Well, what we can do is we can run our current policy, see what it does. It'll generate some trajectories, and then use those trajectories to fit linearized dynamics as an approximation to df dx and df du. You can just fit them with linear regression. This is perhaps a little easier to understand graphically. If you have some policy, and you run that policy maybe 5 times, you get 5 different trajectories. But if you live in an environment that is close to deterministic, and your policy is close to deterministic, these 5 trajectories will look similar. So you can imagine them as a kind of a tube through state space. So it has some thickness to it because there's a little bit of variability, but they all kind of coherently do similar things. So now what you can do is at every time step, you can simply fit a linear approximation, basically literally do linear regression to regress from ST to ST plus 1. And you can do this at every time step separately, and you get linear approximations at every single time step. And remember that LQR actually gives us a linear feedback controller. So it doesn't just give us a sequence of actions, it gives us those big K matrices, and the action is given by big K times X plus little k. So we can actually use that to run a policy in the real world, and it's in fact a closed loop policy. You don't have to use LQR for this, but with LQR it happens to be particularly easy to analyze. So the procedure we're going to discuss is the following. You have some current solution from LQR, which will turn into a distribution, and we'll talk about how to do that. But for now, we can just pretend it's deterministic. We're going to run it on the robot. We're going to collect some trajectories, and we're going to fit our linearized dynamics to those trajectories. So the dynamics will just have a little bit of Gaussian noise, just because you need to model a little bit of error. But the main action is just going to be in the mean, which is some function of the state in action. And remember, we want linearized dynamics, so we'll just say f of xt ut is approximately equal to some matrix times xt plus some matrix times ut. And those matrices will be our approximations to the derivatives. So if we can do this, then we can plug these things into LQR and get back a solution. You're just using the method from last week. And then that will allow us to improve the controller. And then we repeat. Okay, so this is the basic idea, but of course the devil here is in the details. We have a couple of issues. We have to figure out what controller to actually execute here to get the right data so that we can fit these things. And we have to actually figure out how to get this whole procedure not to diverge horribly, because of course this is a local approximation. It's not good globally, and LQR might change our trajectory or change our actions in very drastic ways. So the first problem, choosing which policy to execute, that turns out to actually have a few fairly decent and simple solutions, but the second problem requires a bit more work. So let's start with the first problem. Which controller do we execute? So our goal here is to generate those trajectories that we can use to fit linear approximations to the dynamics. So our iterative LQR procedure gives us these x hats, u hats, k, and little k, which together we can combine to define a linear feedback controller. So even though this looks like quite a few symbols, it's actually very, very simple. It's just the difference between the state you expected and the state you got times some feedback matrix plus some constant terms. So that means that mostly you're following what these constant terms are giving you, but if you deviate from the state that you expected, you're going to correct based on this feedback matrix. Okay, so that's something you can execute in the world. So a very simple version is, well, let's just take an action with probability 1 if it's this action, and probability 0 if it's any other action. So just a deterministic controller that just follows this rule. Does anyone have any idea what the potential problem with this might be? Why might it be a bad idea to execute a fully deterministic policy if we're trying to collect data to fit those dynamics?
You're not exploring.
You're not exploring, yeah. And there's actually a very, well, there's actually a more basic issue too, but besides the fact that you're not exploring, I actually misspoke. So this is actually, ignore this. This is what I was talking about. So the issue is that you're not exploring, but it's actually, it's a numerical issue too. So concretely, if you actually execute these things in the world, remember that afterwards what we'll be doing is we'll be using linear regression to fit our dynamics. So what does linear regression do? Well, it fits a line. So if this is our, imagine this is st comma at. I realize it's a two-dimensional quantity, but I'm going to draw it on one axis. And this is st plus 1. Linear dynamics means that you have some kind of line, right? What do you fit that line to? You fit that line to samples. So if you have nice samples that look like this is a very good linear fit. If you execute a deterministic policy, and your environment is also mostly deterministic, instead of getting nice samples like this, you get a bunch of samples that are all kind of on top of each other. So if you get a bunch of samples that are all on top of each other because all your trajectories did the same thing, then this fit and this fit and this fit all look about equally good. So you want to spread out your samples a little bit. You want to give them a little bit of noise so that you actually see the linear pattern that you can then fit. Because if you don't see that pattern, then you'll have nothing to fit to. Put another way, if you do the same thing 5 times, you don't see which way you should go to improve it. If you get just 5 copies of the same thing, you don't know if this way is good or this way is good. But if they're a little spread out, then you can see the trend. So what you want to do is you want to inject a little bit of noise into this process. And how you choose that noise, there are a few decent choices. You could just heuristically choose to inject a certain amount of variance, and that can actually work fine. There's a neat trick that you can do. You can actually choose that noise based on your Q function. So you remember you have these matrices QUU when you do LQR. If you set your noise to be the inverse of those QUU matrices, that has an intuitive interpretation. It also has a very nice theoretical interpretation. So the intuitive interpretation is that taking this matrix basically amounts to injecting more noise when the action matters less. So the Q function tells you the cost to go. That's the total cost that you'll get for taking an action. So the curvature of the Q function, which is what's represented by that matrix, indicates the sensitivity of the cost to go to your action. If the Q function has very sharp curvature, that means that small changes in action drastically affect your cost to go. If it has low curvature, that means the cost to go is insensitive to your choice of action. So by choosing your noise based on the Q function, that's this part, the quadratic part, you're essentially saying, let's add more noise when the action doesn't matter. Let's add less noise when the choice of action is really, really critical. So that'll keep you away from really terrible regions, but still be as reasonably noisy when you can afford to be noisy. So if U changes Q values a lot, don't add a lot of noise too much. If U changes Q only a little bit, then add more noise. So only act randomly when it minimally affects the cost to go. It's a pretty reasonable rule. And in fact, you can actually prove something about this type of controller when you set the variance to be the inverse of the quadratic component of the Q function. So what you can prove is the following. So LQR minimizes the cost. If you act according to a stochastic policy like this, you can actually prove that this minimizes the cost while maximizing the entropy. So the linear Gaussian solution, this one, actually solves this optimization problem, minimize the expected cost while maximizing the entropy of the policy. Put another way, this is the most random policy you can get while still minimizing cost. This seems a little bit esoteric, but it actually turns out to be really useful later when we talk about KL divergence constraints. So for now, just remember this bit, that if you run LQR but then add a noise based on the inverse of the Q function, you're actually also maximizing entropy. So this is the maximum entropy solution. Act as randomly as possible while minimizing cost. Okay, so now back to our local models. We've talked about how we can choose the actions here. What we do is we follow the LQR solution, but then inject a little bit of noise. We now can talk about how we fit our dynamics. The catch is that we do it with linear regression, so not really all that much there. And then we have to improve our policy. So for fitting the dynamics, the very simple thing we can do is every single time step we get this transition xt, ut, xt plus 1. We see that transition multiple times. And separately at every single time step, we're going to fit our estimate of linear dynamics with linear regression. So that'll get us at every single time step a different A and B matrix so that our dynamics are given by this equation. And then we can plug that into iterative LQR. We can do a little bit better, actually, if we note that in most real physical problems, the dynamics don't just change willy-nilly time step to time step. They're actually strongly correlated. So the dynamics at time step t are pretty similar to the dynamics at time step t plus 1. So we can actually share some of the information across time steps, and that amounts to using a Bayesian linear regression procedure. I won't go into this too much. I just wanted to note this because independently fitting the dynamics at every time step is usually not quite the best idea. But it'll work if you take enough samples. So this second step, using Bayesian linear regression, basically amounts to using your favorite global model, Gaussian process, deep net, whatever, something to fit the global model, but then not actually using that global model, just using it as a prior in Bayesian linear regression for fitting the transition of time step t. And in practice, if you want to use this procedure, you'd probably do something like this because this saves you a lot of sample complexity. But we'll mainly analyze case 1 because it's just simpler to deal with. Okay, but now we come to the real problem with this whole scheme. The real problem is not how you do linear regression or how you generate your actions. The real problem is that the model is local. So this linearized thing, this xt plus 1 equals axt plus b ut, is not an accurate model of how the system works everywhere. It's only accurate in a small region around the data that you saw. And the key to using local models is to impose a constraint that keeps the policy or the plan, the sequence of actions, from going too far away from the region where you collected the data. And this is the main thing that distinguishes this from the model-based RL algorithms that we discussed before the break. So if you fit a linearized estimate of your dynamics like this over here, but the real dynamics are, of course, nonlinear, maybe they look kind of like this. So far away from your data, there's a big error between these things. If you then use the estimated linear dynamics, the blue line, to improve your trajectory, perhaps your LQR solver thinks that you're going to get this. You're going to go to this place. Maybe there's some big reward here. You'll go here and then come back. What you actually get when you go and run this is more like this, because as soon as you hit this region with this big error in your model, something crazy happens and you end up in a place totally different from what you expected. Because it's a local model. The local model is not accurate everywhere. That's the point. It's only accurate in a region around your trajectory distribution. So what you need to do is you need to somehow constrain the solution from LQR or from whatever policy optimization procedure you're using to stay close to where you generated your data. So instead of going way out here, stay close to where this error is going to be small. And that's actually the main thing that we're going to talk about. How do you stay close to an old controller? And the idea here is going to be very similar to the one that we discussed when we talked about things like natural gradient and KL divergence constraints, and it will give us another opportunity to analyze the relationship between KL divergences on trajectory, states, and actions. So for now, our controllers are going to be these linear Gaussian things, although many of the same derivations can hold for other classes of controllers. Our trajectory distribution, just like before, is a big product. Exactly the same product that you saw before, only now I'm using X's and U's, but same exact idea. Initial state, policy, transitions. Multiply them all together, you get a trajectory distribution. So what these pictures are showing, these are showing trajectories. So what you want, intuitively, is you want your new trajectory P of tau that you get after improving your controller to be close to your old trajectory, which I'm going to denote as P bar of tau. Back when we talked about advanced policy gradients, I used pi prime and pi. Now I'm using p and p bar, but similar principle. So you want p to be close to p bar. And now I'm going to analyze this at the level of trajectories, but we'll see that we'll actually end up with a very similar solution. So if the trajectory distributions are close, then hopefully our dynamics will be close too. I mean, in the limit, once they match perfectly, the dynamics are exactly the same. And if they only deviate a little bit, hopefully the error from that linearization will be small. So our goal will be to keep p tau close to p tau close to p tau bar, while still improving our controller, while still improving this thing with LQR. So close in the world of distributions is going to mean KL divergence. So we want the KL divergence between p tau and p bar tau to be bounded by some epsilon. So the epsilon is basically how far we're willing to deviate, and we'll choose epsilon so that it's small enough that the dynamics don't vary too much, but big enough that we can actually improve in a meaningful way. So the trick then will be figuring out how do you enforce this constraint while still improving your controller. It turns out that it's actually, unsurprisingly, very similar to trust regions for policy gradients, which we already talked about before. So the first thing that we're going to do is we're going to write out the definition of the scale divergence, and we're going to massage it into a much more convenient form. And this is a general relationship between trajectory distributions and action distributions. That's, again, one of these things is going to come up in many places in RL. So the KL divergence is the expectation under the distribution on the left-hand side of the difference between the log probabilities of the two distributions. Sometimes it's written as expectation under the first one of the log of the ratio, but the log of a ratio is the difference of logs, of course. So I'm going to write it out this way. And then what I'm going to do is I'm going to substitute the definition for P of tau into this equation. So P of tau and P bar of tau differ only in the policy, right? Because the nature of the world hasn't changed, the initial state hasn't changed, everything still works the same, you just changed how you act. So they actually have all the same terms except for the policy term. Here it's P and here it's P bar. So if I plug in these two definitions for log P tau and log P bar tau, and use the fact that the log of a product is the sum of logs, then what I get inside that expectation is the sum of all the terms here and minus the sum of all the terms here. And of course the initial states are the same and the dynamics are the same, so these all cancel out. So it turns out that if I have the KL divergence between two trajectory distributions, all I really have to account for is the policy terms, the distributions over the actions. So that means that I can plug this back in, and I get the KL divergence between my two trajectories is just the expectation under the distribution on the left side of the KL divergence of the sum of the differences between the log probabilities of their policies. And that's very convenient. That's something that I can actually work with. So I can, just like when I analyzed policy gradient before, I can take the sum outside of the expectation, and then I get a sum over state action marginals of the differences between the probabilities of the actions under the policies. Now, what I'm going to do next is I'm going to collect these terms and do something to this log P term, the first term here. So the second term, the log P bar, it's not going to change. This is just my previous policy. So I might as well treat these log P bar things as constants. They're actually the easy terms. The log P term is going to change as I'm going to optimize my new controller. But what I'm going to note is that if I just pull out the expectation under P of log P here, I can write it equivalently as the expectation under the state marginal of the expectation under the corresponding action distribution of log P. And this inner thing, the expectation under P of u given x, of log P of u given x, is exactly the negative entropy. So that means that I can write out my entire KL divergence like this. It's just the expectation of the negative log probability under the old policy minus the entropy. And if you remember, I mentioned before that when you run LQR and you use that particular controller that has sigma as its variance, where sigma is given by QU inverse, that can be proven to maximize this objective, the expectation under the state marginals of some cost minus the entropy. So that is starting to look awfully similar. If I just kind of pretend that this thing is a cost function, then I can actually minimize the KL divergence using LQR. Of course, minimizing the KL divergence using LQR by itself is not very interesting because it'll just tell me, well, make your new policy the same as your old policy because then you'll have minimum KL divergence. So by itself, that's not that exciting, but it's kind of neat that I can do it. So I just basically say my cost is this thing, and this thing doesn't depend on P, it's constant, so I can just put that in. And that'll get me a solution. So if we can get the KL divergence into our cost somehow, if we can combine it with the thing that we really want, which is to minimize the cost, then we can just use LQR. But of course, this thing is a constraint, and this thing is an objective, so they're not quite the same thing. We need to do a little bit of more work to put them together. So we want the constraint. We want this KL divergence to always be less than or equal to epsilon while we minimize the cost. So what we're going to do is we're going to take the constraint optimization problem, we're going to write out its Lagrangian, and the Lagrangian is going to let us put these things together. Before I get into that, I want to have a little digression, to explain dual gradient descent. First, just to get a sense for whether I'm going to put everyone to sleep, can you raise your hand if you are familiar with how dual gradient descent works? Okay, so just a few people in the class. Good. So, it's going to be kind of boring for you guys, but it'll be probably more interesting for everyone else. So dual gradient descent already came up in a previous lecture very briefly when we talked about advanced policy gradients and enforcing the KL divergence constraint. But now I want to actually go through it in more detail. We're going to use it here to enforce the KL divergence constraint again. And I'm quickly in a few minutes going to go through the basic procedure. So let's forget about trajectories and policies. Let's just say we have some kind of optimization problem, minimize f of x, subject to the constraint that c of x equals 0. So in our case, the objective is the cost, and the constraint is the scale divergence thing. But for now, just have some arbitrary objective and some arbitrary cost. You can write out the Lagrangian of this problem. The Lagrangian, you just get it by taking the objective and adding the constraint times the Lagrange multiplier. And the Lagrangian is a function of two sets of variables, the primal variables, which are x, and the dual variables, which are the Lagrange multipliers. If you write out the Lagrangian and then you take the minimum with respect to the primal variables, you get the dual function. And you can prove in a fairly straightforward way that if you maximize the dual function with respect to the dual variables, plug that into the Lagrangian, then the solution that minimizes with respect to the primal variables will be the solution to your constraint optimization problem. So if you set lambda to be the argmax of g of lambda, that's exactly the Lagrange multiplier that you need to solve your constraint optimization. So then we might ask the question, well, okay, so this is just, convex optimization 101, but in a practical problem where you have some really complicated f of x and some really complicated constraint, how do you do this maximization? How do you maximize with respect to your dual variables? Well, we do it the same way that we do any other kind of optimization in machine learning. We use the gradient, because that's what we know how to do. So we compute the gradient of g of lambda and then climb that gradient. But g of lambda is the minimum of some other function. So that seems like it might be a little tricky for us to compute the gradient. So there's a neat little algebraic trick that we can use here. First, let's write out the dual in a slightly funny way. Well, see, the dual is just the minimum with respect to x, so you can kind of view x as a function of lambda. So for every choice of lambda, the x is whatever minimizes Lagrangian for that lambda. So we can equivalently write it as this function x star of lambda. So x star just minimizes Lagrangian for the dual variable given by lambda. And then you can write out the derivative of the dual with respect to lambda. And you get one term that you get from differentiating through this first argument, and another one that you get by differentiating through the second argument. Differentiating through the second argument is just the derivative of the Lagrangian with respect to lambda. Differentiating through the first argument via the chain rule is dl dx, dx d lambda. Okay? But remember that the way that we obtained x was by taking the argmin of the Lagrangian. So when you minimize a function with respect to some variable, the derivative of that function with respect to that variable is 0. So that means that we know that dl dx star is 0, so this term goes away, and it doesn't matter what that second term is. So that means that the gradient of the dual function is just this part, the derivative of Lagrangian with respect to lambda. And that's very, very simple because Lagrangian is just linear in lambda, so it's just the c of x term. So that's our dual. X star is given by the argmin, and the gradient is just given by the derivative of Lagrangian with respect to lambda, which is just c of x. So this gives us a very convenient procedure for solving a constraint optimization problem. First, we find the x that minimizes the Lagrangian for our current choice of lambda. Then we compute the derivative of the dual with respect to lambda, which we know is just equal to the derivative of the Lagrangian with respect to lambda, which is, in this case, just c of x. And then we take a gradient step on lambda. So it's actually a very simple procedure that allows you to solve constraint optimization problems with complicated constraints and complicated objectives. And then you repeat. So what we're going to do is we're going to basically plug this in order to optimize our cost subject to the constraint on the KL divergence. So this is the constraint optimization problem we want to solve, minimize the cost such that the KL divergence is bounded by epsilon, or equivalently you can write it as maximize the reward subject to the constraint. the KL divergence, as I derived before, is given by the expectation of the log probability of the old policy minus the entropy. So that means that when you form the Lagrangian is just the expectation under your state action marginal of the cost minus Lagrange multiplier times log p bar, and then you have to also subtract the entropy times the dual variable. And then you have this little thing at the end, which is a constant. So now in dual gradient descent, we have to, as step one, we have to find the arg min of this thing with respect to our policy, our p of u given x. So that's kind of the hard part. And then step two is we're going to compute the dual gradient. That's the easy part because it's all linear in lambda, so it's basically just the KL divergence minus epsilon, so that's easy. And then step three is we increment lambda based on the difference. So the only hard part really is step one. Step two and step three are very straightforward. Step one requires us to minimize this thing for a particular fixed lambda with respect to the policy. But of course, I mentioned before that LQR already lets us minimize objectives of this form, some cost minus the entropy. So all we really have to do is we have to take this objective and massage it so that it looks like this. So to do that, all we have to do is we have to divide the whole thing by lambda, because then the coefficient in front of the entropy is 1, and we just plug it in. So we divide the whole thing by lambda, we get this objective. So that basically amounts to saying, let's do LQR, just with a slightly modified cost function. Take your old cost function divided by lambda and subtract log p bar. And intuitively it makes sense, because what lambda is telling you to do, lambda is telling you to stay close to your old policy. So as lambda goes up, you de-emphasize the importance of your cost function, which relatively increases the importance of your previous policy. So I derived all of this for LQR and linear Gaussian dynamics and so on, but the basic idea also holds for other kinds of policies, and the kind of math that we see here is actually quite related to what we saw before with advanced policy gradients when we discussed how we can derive things like trust regions. So we plug this into LQR, get back a solution, then iterate on your dual variable. So step one, set your cost to be 1 over lambda times the old cost minus log p bar. Use LQR to find your new controller using this cost, update your lambda, and then repeat a few times until you've converged. And then you can run your new controller in the real world, collect more samples, update your dynamics, and so forth. So in general, bounding KL divergences between two policies or two controllers, whether they're linear Gaussian or more complex controllers like neural networks, is a very useful thing to do in reinforcement learning. That's how we can stabilize both model-free and model-based reinforcement learning algorithms. And bounding KL divergences between policies is equivalent to bounding KL divergences between their trajectory distributions, because as we saw when we write out the KL divergence, all the terms except for the policy terms cancel out, because of course both the old policy and the new one operate under the same dynamics and the same initial state distribution. So that's basically the idea. In the last minute and a half, I want to show a few videos so that we can kind of relax and wind down a little bit. So what I'm going to show is a little video of this algorithm actually being used to control a robot. So this is a robot that's running exactly the algorithm that I just described. There's no neural nets, no deep RL or anything. It's just running that whole LQR thing. And it's playing with sort of age-appropriate toys to try to stack this Lego block over here. So what this is showing is actually, it's 10x real time, but this is actually the live learning process. And you can see that roughly every 5 trials, the behavior changes. And that's because every 5 trials, it refits those linear dynamics, updates the policy using that KL divergence constraint, and then runs the new policy. So it runs each policy for 5 trials. And you can actually see, when it pauses a little bit, that's when it's thinking, that's when it's updating the controller. So it's iteratively improving every 5 trials there. Okay. Yeah, here's another video. And maybe while this is playing, if anyone has any questions about anything I discussed in today's lecture. And if not, then we can wrap up. Okay, so see you all on Friday for the discussion of advanced model-based RL with images and probabilistic models.